Next page. Because that's actually technically the lesson. Everything after this is practice, but historically people have gotten jammed up pretty significantly on number 2. So I figured it'd be a good idea to take you through that one. All right, Searchlight is positioned 10 meters from a sidewalk. And really the reason I think people get jammed up on this one is because it just can't visualize the situation. So I'll draw the diagram for you, it should help. Person is walking along the sidewalk at a constant speed of 2 meters per second. Searchlight rotates so that it shines on the person. Find and interpret the rate at which the searchlight rotates when the person is 25 meters from the searchlight. All right. So I'm going to draw a top view of this situation. You have a sidewalk. Just kind of make it look sidewalky. And get a little curb. And put one of those vents that I'm always afraid to walk on. Yeah, those things terrify me. Let's just do a couple of, yeah, like that. Throwing a little fire hydrant action here. That's fire hydrant. And of course we need the person walking, right? Because the person's walking. So I'm gonna make him a purple individual. So that's unfortunate. And really happy because he just decimated half of the galaxy. All right, and then over here we have a searchlight, again, top view. So that one is a searchlight.
I don't like in my casual walks encounter searchlights.
What's that?
I don't know my casual sidewalk outings encounter searchlights very often.
Yeah.
Where is this person?
Clearly near a prison of some kind. So
Fun little walk day.
a nice stroll by Sing Sing, I guess. Yeah, actually I've never been there, so I don't know. But one of the guest speakers actually teaches math over at Sing Sing. So he teaches math to prison inmates. That was Gary, the second presenter.
And we're like, okay, drop you off. Like, no.
And you freak out, but in reality, since it doesn't work that way, it was an empty threat, but it probably worked in the moment.
No, it isn't.
All right, so the searchlight is 10 meters from the sidewalk. So let's do that. Let's just draw a little line segment. I'm gonna write it as a unitless measure. I'm just gonna verify that all the units are the same. We're talking in terms of meters. And I took a test on this when I was a student. Got everything right except for one question, where the teacher, the wise guy that he was, meters, centimeters per second. Completely whiffed on it. And I got an answer that was absurd, but I didn't bother checking it to see if it made any sense. And so I lost some credit for that. So, yeah, that could happen. I mean, I'm not, well, it's not going to happen. It could happen in life, I suppose. There could be a trick question. It's not going to happen in this class. So, constant speed. So dx dt is equal to 2. And again, I'm just writing it unitless because we're confirming that it's pretty okay. All right. Find and interpret the rate at which the searchlight rotates when the person is 25 meters from the searchlight. So what this is telling us is that at some point down the line, you know, so Thanos is over here somewhere. I don't think I have, this is as close as I have to gold, so I'll just do that real quick. Get in there. So. Let's get one of those. And one of those bad boys. Get one of that. We're gonna need.
It's like his weird chin.
Yeah, the chin is key.
Yeah, I could pop in a little chin action here.
Oh, it's Thanos.
So it's basically like, instead of legit beard, it's legit chin. What colors am I missing here? Yeah, I need two more, I just can't. Oh, one's purple. Power Stone, yep.
You have the red one.
Yeah, I got reality, I got space, time, oh, orange.
It's there.
It's basically
I'll just kind of put it off on the side here.
the rainbow.
What is that?
You could have drawn like a white circle, so like inside it's orange. Make it like a
True.
on that side.
That's like advanced art.
Yeah, next time.
This problem is we live and we learn.
Yeah.
Oh, like right on the other.
So at some point later on down the line, you're going to be 25 meters away from the searchlight. So that's going to be related to some angle theta. So we have a horizontal distance x. We have a vertical, it's not really vertical, just based on the way I drew it, it's vertical. And we have a hypotenuse. So, you know, based on the scenario and the problem, it doesn't seem like it would be a right triangle that you're looking at, but the way I drew it all out, it makes it pretty clear that it's a right triangle. Now, we are talking about the rate at which the searchlight rotates. So that's talking about an angular measure, right? So it's asking us for d theta dt. All right, so whereas in some of the previous problems, we were looking at the Pythagorean theorem, now in this case we're looking at SOHCAHTOA. So it's good news, bad news. The good news is you have 6 possible ratios that you can create. The bad news is you have 6 possible ratios you can create, right? So the reason why that would be bad is if you choose poorly, you could end up going in circles and it won't be a wonderful feeling. So that being said, I do need to have a dx dt here. Where did that come from?
The orange?
Yeah, that little stray business
I
there.
don't know if that was like, I don't know.
Maybe it was like your wrist when you were drawing it.
Oh. That was weird. All right, so it's a necessity that I have an x in whatever ratio I choose. All right, because in order to create a dx dt, my original function should have an x in it. All right, that's the opposite side of my triangle. So out of SOHCAHT and TOA and all the reciprocals, I want to have one that incorporates an O. All right, so that could be the sine function or the tangent function. All right. Then you also have to think about, well, I have other pieces of information here. I have a y and I have an r. Now, I would prefer to incorporate the y, if possible. All right. The reason why I would do that is because this is a constant distance. This distance is not changing. The searchlight is always 10 meters away from the sidewalk. All right. If you incorporate the r, you're going to create a dr dt in your derivative. You don't have information about that, nor are you looking for that. All right, so it's probably not the best way to go. So in this case, I have an opposite side, and I have an adjacent side. So I'm going to go with the tangent ratio. All right, so it goes back to the good news, bad news kind of thing. Opposite over adjacent.
So you use that instead of the hypotenuse? Wait, why do you use it instead of the hypotenuse? 'Cause you already
We have values for both of them, but this is a variable value. This
Oh,
depends on where he is.
got it.
This one is not changing, so we can take advantage of that. All right. So the good news, bad news again. If you select the incorrect ratio, all right, you'll find out at some point which point you go back and choose a different one. All right. So the only thing that it will be is a waste of time. You'll still get it right eventually. All right. You just have to persevere through all that. All right. So tangent theta is equal to the opposite side, which is x, over the adjacent side, which is y. All right, so I have to take the derivative of this. All right, so left-hand side's easy enough. What's the derivative of tangent? Secant squared theta times d whatever dt, in this case theta, exactly. Now, on the right-hand side, we have a quotient of two functions. So we have a numerator, we have a denominator. So quotient of two functions, a little low d high minus high d low business. So low y, d high would be what? 1 times dx dt. So I'll just write dx dt. Minus the high, which is x, d low, dy dt. Over the denominator squared, which is just y squared. All right, so we're applying the quotient rule here. Again, nothing new, but that doesn't mean it's going to always be easy. All right, so now we're going to go through and plug in the information that we know, and then we'll make some inferences, and then we'll go from there. Left-hand side looks impossible at this point. You're like, how am I supposed to figure out secant squared? I'll show you a very easy way in a second. On the right-hand side, the y value was given. dx dt was given. X we don't know, but we can figure it out if we need to. Again, y is given. All right. So, very important. This guy right here. That's related to the rate, well, it's the rate of change of the y value. Is the y value changing? No. So this should be equal to what? 0. Y is constant. That means the rate of change equals 0. So now it doesn't matter what x is. We could have figured it out if we wanted to. Little Pythagorean theorem. But, oh, actually they told us it's 25 anyway. Oh no, they didn't. That's something else. All right, yeah, so we didn't need it anyway, so it doesn't make a difference. The whole right-hand side simplifies down to what, 1/5?
Yeah.
So now I just need to get this secant squared part of it. All right, well, secant squared theta is secant theta squared. I know that's mind-boggling. It's like, whoa, new information. More importantly, it's a ratio. All right, that ratio is the hypotenuse divided by the adjacent. Right, because secant is a reciprocal of cosine. Cosine is adjacent over hypotenuse, so secant would be hypotenuse over adjacent. All right, so I know the hypotenuse, it's 25. And I know the adjacent is 10. Okay, just get that right from the picture. Hypotenuse, adjacent, 25 over 10. Could simplify a little bit. So 5/2, right? Squared times d theta dt is equal to 1/5, which is 25/4 d theta dt, multiplied by reciprocals, and we get d theta dt equal to 4 over 125. And the units here are radians per second. All right. And it's a lot like some of the other problems that we did where, you know, you could put it in decimal form, but I don't think it's going to be any more meaningful than it would be in fraction form. That being said, you may want to convert this over to degrees just so you can actually get a decent sense of what it's talking about. Because people are pretty good at conceptualizing what degrees look like in terms of a movement. Radians not so much, unless they're like clean radians like pi over 2 or pi or something like that. But 4 over 125, I don't know. That doesn't seem to be something that you can conceptualize off the top. Aside from saying small, like a small movement every second, but if I needed to, take my 4 over 125. And this is just for your benefit, just to get a sense of what this looks like. Multiply it. What's the conversion factor for radians to degrees? What do we multiply by? 180 over pi. All right. So what that's saying is about 2 degrees, roughly 2 degrees every second. Right. So that's like, here's 1 like, beep, every second. Yeah, it seems to be very slow. If you want to get a true sense, because you could think of a full turn, divide that into 360. 196 seconds, yeah. So you're talking about a little bit more than 3 minutes to get one full rotation of the searchlight. So that's a fairly lengthy period of time. So this isn't like a strobe that's going very rapidly. It's a searchlight that's sweeping at a slow rate through an area. All right. So if you think of like a spy movie, when they're trying to time their movements to get from one part of a courtyard to the other, and they're just kind of going behind obstacles to protect themselves from like whoever the guard is up on top. And, you know, they're just saying, okay, on 3, go, and then they would run, and then the searchlight would come through, sweep through that area, and then they would go to the next obstacle and so on. All right, so it's more like that scenario than something that's like a siren spinning around very rapidly. All right. So anyway, that should prepare you for all the remaining problems.